In this lecture, we will discuss the discrete time Fourier transform. This transform is based on what you learned in analog signal processing, so we will start there. Here, you can see the Fourier transform, which you should know from analog signal processing. In this course, we use capital omega to represent analog frequencies. Below the Fourier transform, we have the discrete time Fourier transform. You'll notice that the DTFT is simply an analogy into discrete time. We change the integral to summation to accommodate this discrete nature, and we use samples rather than time t, and we use lowercase omega to represent digital frequencies. The DTFT then creates a continuous function x sub d of omega. To reverse the process of the Fourier transform, we use the inverse DTFT. And essentially we just change our variables again from capital omega to lower omega. And we also change the range of the integral from infinities to pi's. I'll explain why we change the integral by showing an example DTFT. On the top graph, you see the magnitude of the DTFT. On the bottom graph, you see the phase. Notice that both graphs are periodic with period 2 pi. This periodic nature of the DTFT is caused by our sampling of x sub a of t. When we sampled x sub a of t, we place a limit on the range of digital frequencies in the signal. The sampling frequency corresponds to 2 pi. So the highest frequency in our signal is 1/2 the sampling frequency, or pi. Since the frequencies of real signals are symmetric about 0, we can integrate from negative pi to pi and integrate over every negative and positive frequency in the DTFT. This graph also shows us two important properties of the DTFT. The magnitude of the DTFT of every real signal is evenly symmetric. The phase of the DTFT of every real signal is oddly symmetric. For the remainder of the lecture, I will briefly describe some other important properties of the DTFT. The DTFT is a linear function. This means that when you add discrete time signals together, you can obtain their joint DTFT by adding their separate DTFT functions. If you multiply a discrete time signal by a constant, you can obtain the modified signal's DTFT by multiplying its original DTFT by the same constant. These two principles can also be applied together. If you multiply the DTFT by a constant phase factor, such as e to the j omega k, you will time shift the original signal x of n by that same factor of k samples. I want to make sure that you notice that shifting a signal in time does not affect the magnitude of the DTFT. Shifting affects only the phase. The modulation property is very similar to the shifting property, because if you multiply the discrete time signal by a constant factor of e to the j omega naught n, you will modulate the DTFT, or shift it to the right by omega naught. The final two properties are useful because they allow us to simplify our calculations. The convolution property tells us that we can choose to multiply the DTFTs of x and h rather than convolving the discrete time signals of x and h. We use h here because h corresponds to the filter that we use to create y. We'll discuss h in greater depth later. Parseval's theorem tells us that we can calculate the energy in a signal by using either the discrete time signal or its DTFT. For both these properties, you want to look at the DTFT and the discrete time signal, and use whichever one will be easier for you to calculate.